Good morning, everyone. I'm Niall Hardy. I'm a surgical research fellow from Dublin in Ireland, and I'm delighted to present some of my work on classification of significant rectal lesions with artificial intelligence. I have no personal disclosures. It's a funded project as part of Enterprise Ireland, a government body. Some of the other co-authors have some collaborations with other institutions. So fluorescence-guided surgery involves the injection of a dye, ICG here, intravascularly. It travels around the vascular system. Here it is at colorectal surgery. It's indicating well-perfused colon on the left there by the green colour and poorly perfused on the right. It's also been used to detect cancer, as it's been known to non-selectively stain malignant lesions. Here it is at liver tumour. This dye has been given a number of hours or days even in advance. It's washed systemically through, washes out of the cancer, and you come then at your time of surgery and you hope it points you in the right direction. And this is kind of a cartoon of that. But this really has proven unpredictable. It's required long durations of planning, lots of issues with regards to false positives, it traps in regions that are not cancer, and it's never been applied endoscopically to rectal lesions. So going back to that original cartoon there, if you look at the very end picture here, where the dye is in the cancer and washed out elsewhere, actually the story begins within a number of seconds of when you give the dye. It washes in initially throughout the entire system, then penetrates into the tumour, and then starts to wash out of the healthy tissue. So really, within a number of seconds of giving the dye, there's a wealth of information to be gleaned if you're looking in the right place and you have the tools to extract valuable information. So what does that look like? This is a rectal cancer. The infrared camera is introduced transanally. We've given the dye. We're waiting. It's washing systemically. You see it in the foreground, it starts to come in. Then it starts to come into the tumour. Eventually, the whole thing goes either green or white, whichever one you're looking at. It happens at different speeds. And as a human, it's very, very difficult to make sense of all of this. But with artificial intelligence, we were able to tell within that time frame there that there was a cancer within this lesion. So how do we do that? We've a bespoke tracker. I'm picking two regions of interest within the lesion here, two comparator regions within healthy surrounding tissue. And what I start to do is extract a fluorescence over time curve, the change in intensity in those regions. So you can see here the graphs are starting to appear. I think we prefer to look at graphs as humans. We can kind of start to see two camps are appearing here. There's the yellow and the green, the red and the blue. But still, it's quite difficult. It's certainly intraoperatively, if you were looking at these, there'd be a lot of information coming at you. These are two sample lesions, healthy, and the lesion itself, at least two regions of interest per lesion, so that we have a comparison. And then we want to start extracting features from these curves so that we can analyze them. And the features that we pick out are things like the time from inflow starting to the peak, the time ratio, which is half of that, upslope and downslope to various different time points, 50 seconds, 100 seconds, 400 seconds, as well as kurtosis. These are measures or appearances of the curves. And the point of this is all explainable and interpretable with regards to machine learning. We know these points that we're picking out. We know why we're picking them out. They're based on flow. And then we're able to interpret the results a little bit more meaningfully, I suppose, than something like deep learning, where we often throw these pictures in and we don't understand truly the information that's coming back out. And then obviously we have to put these through a classification algorithm once we've extracted everything. So with regards to classification algorithms, as I mentioned, we wanted to exclude the neural networks or the more complex systems and stick to a subset of machine learning algorithms. K-nearest neighbor, or KNN, was identified as the most efficient classifier for this use by AutoML. It's just a system that looks through a number of different hyperparameters when you input your data and basically tells you what system will classify it the best. And the feature, or the measure of success that we picked, is the area under the rock curve. And this is a kind of a combination or a hybrid of sensitivity and specificity. We use five-fold cross-validation. This is a machine learning technique to split your training and your testing data sets so that you can increase your numbers, and an 80-20 training to testing set. And importantly, we wanted to classify these curves in 3 ways: healthy, benign, or cancer. The patients that we did this on, they're pretty standard range of patients, 65, collected over a 3-year period at multiple different institutions in Ireland, in Amsterdam, as well as in the UK. And importantly, these were all significant rectal lesions. These were referred for surgical opinion, so they were either known cancers or something that there was a consideration there may be cancer or needed a surgical resection. When we look at our results, of the 65 patients that we assessed, we were able to include 63. 2 videos we had to exclude as we weren't able to get a control healthy region tracing in the video. And that gave us 419 regions of interest, individual curves. And the AOC area under the curve score is 0.93 for all 63 patients. So just to put that in context, 1.0 is perfect, and greater than 0.9 is considered excellent. So really, across all of these patients, this classifier is performing extremely well. Coming back to that picture that I showed you earlier on a patient level basis, this is the kind of thing you get. Of the regions that we've drawn, it gives you an output. Does it think it's healthy, cancer, or benign? And how likely or how sure it is of that prediction. Looking backwards then in time, we mentioned one of the issues earlier on is that you have to look for long periods of time initially. With this system, actually within about 100 seconds, and certainly 200 seconds of giving the dye, we were able to get excellent results for prediction of cancer, healthy or benign. This is a fluorescence microscopy image, so this is taken about an hour and a half, and these are cancerous regions on the left in the H&E, and you can see here the fluorescent dye is trapping, but we don't have to wait this long. We're predicting within seconds this final picture with a very, very good results. The next step obviously then is to move on to full lesion classification. This is again another rectal tumour. If we stabilize this image and extract a fluorescence curve for every single pixel on the screen, these are just 4 example pixels on the right with X and Y coordinates, so there are many hundreds of thousands on the left screen, and then redisplay them based on the perfusion profiles, what's been going on over the last few minutes. You can see here we start to find areas where the metabolic activity or the perfusion activity is altered, and of course it's mostly within the cancer. The lesion that we looked at earlier on, again, looking at 2D imaging, 2D boundary mapping, we can start to see the dye being trapped within the lesion here over time, and we can display these in the operating room. So the conclusions: colorectal tissue can be characterized by its dynamic perfusion patterns using easily interpretable features, but only easy to machines. This will have important clinical uses, identifying locations of high-yield biopsy, accelerating patient pathway towards the correct definitive care, delineation of tumour margins so that we know where to cut and when to cut. And importantly next, this is now moving on to a prospective multi-centre trial which is commissioned. It's the Classica, which will be performed as part of Horizon Europe. So thank you very much. I appreciate any questions.